Over the course of the next few weeks, we'll be getting into statistical inference. This is how we infer features of the population from features of our sample. Before we get into that, we'll cover the central limit theorem. This is one of the most important tools in statistics. A lot of things follow or seem to follow a normal distribution, and just about every other distribution we use is related to it in some way. We also make all kinds of assumptions about normality when we're modeling things, and usually what's justifying these assumptions is the central limit theorem. The central limit theorem says that as the sample size increases, the distribution of the sample mean tends toward a normal distribution. In order to understand the central limit theorem, we need to understand the concept of a sampling distribution for a sample statistic. There are three distributions we're concerned with. First, there's the population distribution. This is the one we're studying. This is the one we actually care about. But since we can't usually measure every element of a population or take a census, if you remember that term, since we can't do that, we have to take a sample. The sample distribution describes how our sample is made up. And our hope is that it resembles the population, so that it can tell us something about the population. But we never really know for sure. And this uncertainty is where statistical inference comes in. Our goal will be to make probability statements about all this stuff. And this is where the sampling distribution comes in. A sampling distribution is a probability distribution that specifies the probabilities of all the different values that a sample statistic can take on. Today, we'll focus on the sampling distribution of the sample mean. Let me give you an example of what a sampling distribution looks like. I have to make this really simple because there are usually so many ways that a statistic can come out that it would take forever to list them all. Say you take a sample of size 2 from the set 1, 2, 3, and you sample without replacement, so you're not putting the number back in once you've drawn it. So you take this sample, and the two numbers you get are 1 and 2. This is what the population distribution looks like. There's 1, 1, 1, 2, and 1, 3. And this can be viewed as a probability distribution in that if we randomly choose an element from this set, we have these probabilities. The probability that the number you draw is 1 is 1/3. The probability that the number you draw is less than 3 is 2/3, and so forth. And again, this is the population distribution. And here is the sample distribution. Our sample was 1, 2, so the distribution is 1, 1, 1, 2, and 0, 3s. The sample distribution is usually what we're looking at when we draw a histogram, and we would like it to resemble a histogram of the population. That brings us to the sampling distribution. Remember, a statistic is a number computed from the sample. Since the sample's values are random, the statistic's values are random. There's a probability distribution associated with each value that a statistic can attain. The sampling distribution tells us those probabilities. In this case, there are 6 possible samples we could have drawn. This column here is called the sample space, by the way. The sample space is the set of all possible outcomes for an experiment. If you sample 2 numbers from the set 1, 2, 3 without replacement, these are all the possible outcomes. In the second column here, we have the mean for each outcome. When the sample is 1, 2, the mean is 1 plus 2 over 2, and that's 3/2. When the sample is 3, 1, the mean is 3 plus 1 over 2, and that's 2. This table over here is pointing out that there are 2 ways to get each possible sample mean. 2 out of 6 is 1/3. There is a 1/3 probability for each outcome. This is called the sampling distribution. The sampling distribution is a probability distribution that specifies the probability for each value of a sample statistic. In this really simple example, the sample mean turned out to have a discrete uniform distribution. There are 3 possibilities, and they're all equally likely. What we'll get to next, the central limit theorem, says that in general, the sampling distribution of the sample mean has a normal distribution. We can use p-norm and normal curves to find probabilities regarding the sample mean. The central limit theorem describes the asymptotic behavior of the sample mean. If we take a sample of size n from a population with mean mu and standard deviation sigma, then as n approaches infinity, the sampling distribution of the sample mean approaches a normal distribution with mean mu and standard deviation sigma divided by the square root of n. Usually, we sample from a large population, so in practice, n will be much smaller than the population. When n gets large enough, and it doesn't have to be that big, if n equals 30 or even 25 in most cases, then we can treat the sample mean as if it comes from this normal distribution. And this squiggle with the dot over it is just to be formal. I usually won't bother with the dot, and we can just accept the fact that the mean has this distribution. But just to be clear, the sample means distribution is approximately normal, and it gets closer and closer to normality as the sample size increases. One thing I want to point out, we have a normal distribution centered at the population mean. And if you recall, decreasing the standard deviation makes the curve thinner, where the area is more clustered around the mean. You're less likely to draw values far from the mean. If you look at the standard deviation of the sample mean here, the denominator is the square root of n, and sigma is a constant. As n gets bigger, this fraction becomes smaller. So bigger n gives you a smaller standard deviation for the sample mean. It becomes more likely that your sample mean is close to the true mean. Increasing sample size increases precision. If the population itself is normal, then the sample mean will be normal no matter what. But usually we don't know the population distribution, and when it's anything other than normal, we need the central limit theorem. Like I mentioned earlier, in most cases, the sampling distribution starts to look normal when n equals 30, and often it's less. N equals 30 is a common rule of thumb found in a lot of textbooks, including the one we're using. So we'll follow that. If the sample mean is 30 or more and there are no extreme outliers, we'll just assume that the sample mean is normal with mean mu and standard deviation sigma divided by the square root of n. Finally, one error I've seen several times is when people think that the sample becomes more normal as you increase the sample size.
It's the sample mean whose distribution becomes more normal. As you increase the sample size, the sample itself should look more like the population, and the population could be anything. It doesn't have to be normal.